Well, this review session seems like it might be kind of long. I'll warn you there are quite a few slides, but I promise you this test is kind of a similar length to the previous tests you've taken. One of the things we covered in this unit was our sun, and of course what our sun is doing is fusing hydrogen. These could be two little hydrogen atoms to form helium. Now, they're not connecting because actually there's not enough pressure and temperature in that case. But in the core of our sun, there's a question about this, there's sufficient temperature. With high temperature, they're going very fast, and there's sufficient pressure. With pressure, they're very close to go ahead and have hydrogen atoms fuse to form helium. So this is kind of a look at the fusion that's going on in the core of our sun. These four little things, of course the P stands for proton, would be actually not just 2 hydrogen protons, but 4 hydrogen protons that ultimately go to form 1 helium atom and a bunch of energy. And then this kind of just shows the details. So, of course, we talked about the fact that our sun is losing mass, and it's losing mass according to E is equal to mc squared. For some of that mass, you take it times the speed of light squared, and that's the amount of energy that's being produced. So our sun is actually losing a little bit of matter all the time. Specifically, each second it's losing 600 million tons. Wait, sorry, 4 million tons each second. Hydrostatic equilibrium. So our sun is at a kind of a happy spot. It actually has gravity pulling in on it, but it has an outward going pressure due to actually associated with the fusion that's happening in its core. So it's not shrinking, nor is it expanding. That's what hydrostatic equilibrium is. I have a couple slides about this. This is that random walk of, this would be energy, the core might be down here, and these little squiggles are energy from the fusion, and it bumps up against matter in the sun, and it just kind of keeps being randomly transferred. So they call it the random walk. This is actually in the radiative zone. I'm going to show you layers of the sun. So this is showing you the random walk, and down here it shows you that random walk from the energy from the core outward to the surface of the sun could take anywhere from 100,000 years to 1,000,000 years once it's created to find its way out to the surface of the sun. I think that is so cool. No pun intended. And then we talked about the layers of the sun. We have 3 outer layers of the sun. We are actually in an odd way associated in the sun's atmosphere. We heard that on a video this semester, and I thought that was interesting. But if we talk about the atmosphere of the sun, we have the outermost layer of the sun's atmosphere called the corona, we can see during an eclipse, and then closer to the sun's surface we have the chromosphere and then the photosphere. And remember, the weird thing is, if you were to tell me temperature-wise, the corona is the hottest. The corona is not as hot as the core of the sun, obviously, but it's the hottest atmospheric layer of the sun. And then we hit the beyond, well, let's see. Now these next ones go from the inside out. So of course we have the core, where the nuclear fusion is going on, and beyond the core we have the radiative zone, or radiation zone, where the random walk is happening, and then we have the convection zone, kind of like blobs of warm plasma actually from the sun rising. It cools down and it sinks, and so that's the convection zone. And when I think of the convection zone, I actually kind of then think of it bumping up against the photosphere, and we kind of see those granules. So it all kind of makes sense. So one of the cool things, no pun intended, about the sun is this outgoing pressure called solar wind. And collectively, the solar wind creates what we call the heliosphere. So the heliosphere is that big balloon kind of going, I think of the heliosphere as actually going beyond remember we talked about the Kuiper belt and the Oort cloud. So the heliosphere, it's very big. I can't remember. I'm kind of losing track of what the test questions are, but be sure to compare this review sheet with this review video with your review sheet. So the limb, anybody sometimes talks about the limb of the sun. They're talking about the disk, the edge of the disk of the sun that we see. Of course, never look at the sun with your bare eyes. Always have protection. And so when we look at the surface of the sun, we are seeing the photosphere, and that's called the limb of the sun. And here we call it these granules. And actually in class we looked at a little video where these granules aren't static. They're kind of creepy looking. They kind of change their shape, but granules are a feature of the sun that are always there. And they are associated with, I believe, the convection cell, the convection cells and the convection layer right underneath the photosphere. So here we have hot plasma rising, cooling down, and so these ridges that we see are cooler areas on the sun. So again, it's kind of dynamic. Then on to the next part. So space weather. The space weather means what the sun's activity is. And remember, the sun can be quiet or the sun can be active. And so one of the things you're going to want to be able to do is talk about a quiet sun or an active sun. Well, let me rephrase that. One of the things you need to be able to do is talk about features of the sun that are always there, whether it's quiet or active, and then features that are only there when it's active. Let's put it that way. So whether it's active or quiet, are granules. We saw associated with the photosphere, supergranules, spicules, solar wind. Things that are associated with an active sun then would be these, and I've got some pictures I think coming up of these. Sunspots. Sometimes come in sunspot groups, plages, filaments, prominences, coronal holes, and the big granny daddy of them all, which has actually charged particles, hopefully not with us in its path, the Earth in its path, but the coronal mass ejections, or CMEs. I'm being attacked by my cat right now. So features of an active sun, remember we're going to see maybe it's right here. Oops, sorry. They actually go with an 11-year cycle, and the features of an active sun are associated with its crazy electromagnetic field. So this is actually showing you an active event. Again, I kind of said in lecture, I'm not going to show you any pictures and say, oh, is that a coronal mass ejection or is that a solar flare? Okay, I don't think it's fair to do. But I see a caption here. Well, actually, these over here are coronal mass ejections, or a coronal mass ejection. And you can see how you can see the material leaving the sun and actually getting to the Earth. And of course, you couldn't see this little thing right here is the Earth, and this is the Earth's magnetic field. And you can see it kind of buffering the Earth against the charged particles coming from the sun. So I'm gonna have to squirt my hat. Okay, we'll try that. So the charged particles come in, I believe, about 8 minutes. Wait, no. The energy comes in about 8 minutes, and the charged particles there's a delay. So, okay, so the 11-year cycle actually is from 7 to 15 years, but about every 11 years you have a peak. And right now, remember, actually, for those of you who went out and looked at a few sunspots this semester, it's kind of hard to see. We are approaching a solar minimum. So with an active sun, you should expect to see sunspots groups, solar flares, prominences, filaments, plages, coronal holes, and coronal mass ejections. The reason we care about the activity of the sun, and the cool word is assets. We have assets in outer space, assets including like the International Space Station with people aboard, the Hubble Space Telescope, other things that we need to know what the sun's cycle is, and can we expect coronal mass ejection, for example, that would compromise our assets out there. Okay. All right. This picture actually then is related to space weather. This is back on Earth, and this is the picture of a Northern Lights on my bucket list. And the Northern Lights are where the sun has been active and has sent an extra dose of charged particles that the Earth's magnetic field can't accommodate, and so the overload of charged particles fall down through our magnetic poles, north and south, and so they make these pretty colors. On to the next part. So in the next part, we just kind of started talking about stars in general. So one of the things about a star is you might want to know how luminous it is. Now, luminosity is the amount of energy it's pumping out per second. Okay, it's measured in watts, just like a light bulb is measured in watts, luminosity. Now, apparent brightness then, apparent brightness, lowercase m, is how bright that star appears to us. And like you guys told me in lecture, how bright it appears is related to its luminosity, how much energy it's pumping out, and its distance to us. And we actually have a little equation to relate that coming up. So, because one of the things about it, this is kind of showing you the dilution of light as it goes. And the dilution of light is by what we call the square of the distance of the object from that source. So yep, apparent brightness, how bright something appears, lowercase m, depends upon how much energy the star or whatever is pumping out versus the distance it is from us. So we have this brightness scale, apparent brightness scale, apparent magnitude, lowercase m. Now remember, I feel like it's a little bit backwards. The higher the m, the higher the apparent brightness, then actually the dimmer the object is. And it's all based upon a scale of +1 to +6. +1 being the brightest thing at the time that they base, the brightest star anyway, that they base their observations on, and a +6 being the dimmest one. And remember that if somebody says like it's a +1 versus a +2 magnitude, two different objects, remember that's a factor of 10 actually dimmer for that +2 object. And then also remember we have negative magnitude numbers because we actually have things that are brighter than +6. Makes sense. This then actually is, I don't know which of these three, there's three equations here, 1, 2, 3. And which of these three would you want? Well, they're all saying the same thing. And brightness, remember I have over here, brightness means apparent magnitude. So lowercase m, brightness, how bright something appears, is you take the luminosity, how much energy it's pumping out, where it's located, and you divide by 4 pi times the distance that it is from us squared. This kind of leads us to some kind of cool sort of ways of figuring out distance. So for instance, down here, I can know the distance to a star if I know or understand it's how much energy it's pumping out, and I divide by its 4 pi apparent brightness, take the square root of that. So this actually is a way of getting to distances of stars. Then we have this other brightness scale. And again, I said, don't blame me, I wish they would have had a different variable, but it's an uppercase M. So absolute magnitude is what I call kind of a normalizing process. It's to recognize that stars, that the distance to stars is a player in how bright they appear. So absolute magnitude then actually relocates the object 1 parsec from us and then again looks at how bright it is and gives it a new number. Let's see, I have an example here. So for instance, our sun is like a -27 apparent magnitude, apparent brightness, which makes sense because it's so bright. But if we were to relocate, and I don't suggest us doing this, the sun, instead of 1 AU from us, 3.26 light years from us, it now would appear as if it were a +4.9, which is a lot dimmer than -26. So then that means its absolute magnitude is +4.9. Okay. So down here actually, and I didn't emphasize it much in lecture, but remember when we were drawing those HR diagrams and along the y-axis there on the left, I kept putting luminosity. Well, so actually since absolute magnitude, how do I say this? Since absolute magnitude normalizes for distance, absolute magnitude and luminosity actually correlate, or they mean the same thing. So sometimes on HR diagrams along the y-axis, you'll see absolute magnitude. Okay, so still talking about stars, we talked about these lovely ladies, and they came up with 7 spectral types, and you're going to want to know the O, B, A, F, G, K, M. So O, be a fine guy, kiss me. Of course, O is hottest and M is coolest stars. Looking at the stellar spectra, I just think that is so cool. This is talking about how we can actually gauge that stars are moving. So this over here, of course, sun, we're orbiting the sun. Now, if we were to look out here at the star, this star can have what we call radial velocity. And you should see radial velocity. Radial velocity means it's either moving away or moving towards us. And we can actually use the Doppler effect to know that sort of motion, radial motion. This proper motion, or they call transverse velocity here, this proper motion, we can actually just kind of see that relative to background stars. Does that make sense? So those are the two ways of seeing stars moving relative to our position. So this was a slide to kind of show you, remember the Doppler effect. If something is moving towards us, you're going to see a redshift. Now, this actually, you can't see much of a change, but look at this as a stationary object, and look just a little bit how these lines are shifted a little bit to the red, not much. So that would be what? Moving away from us. We'll be talking more about redshifts so as we talk about our universe and galaxies. Blue shift is something moving towards us. Can you kind of see how these spectral lines are shifted just a little bit over here to the left, okay, to shorter wavelengths compared to the stationary source. Okay, so a way that we can determine distances to stars, another way, in addition to comparing their what their absolute magnitude or luminosity to their apparent magnitude, is this thing called stellar parallax. And this is the one where I said if you put your finger in front of your nose and wink one eye shut and the other eye shut, and you kind of see then if it's close to your nose, then you see a big shift in the background, your finger relative to the background. If you extend your arm, you see less of a shift. So actually, these are kind of showing you two stars. This left one is a farther away star, and this right one here is a closer star. And you can see where the farther away star has, this is the parallax shift, which is a fair bit. That bright star relative to the background, you can kind of see it be located in different positions as the Earth orbits the sun. Here you can see a bigger shift, and that's because the star is closer. So we're going to call this a parallax angle. So the bigger the parallax angle, then the closer the star. Okay, so that's how that works. We said that most stars actually have a companion, which is kind of fun. If not 2, 3, or even 4 stars that were born about the same time, and they have a common center of mass. The gravity is all kind of holding them together. And so stars then, we have the visible binary where you look up and you can literally see 2 stars. And then we have these more, what I call elusive binaries, that you really can't tell that there are 2 stars there. So you tell that the way you understand there are 2 stars there is the type of binary they are. So for instance, spectroscopic binaries, we use the stellar spectra of the stars to see that actually they are moving around a common center of mass. So for instance, down here we could see, I was going to say I didn't have enough slide to kind of break this out, but I didn't bring those in. But we have kind of a red star and a blue star, and we can't see both red, blue, and the blue star, but we can actually see the blue star as it's moving towards us, we'll get a blue shift. As it's moving away from us, we'll get a red shift. So you can kind of see little wiggles in their stellar spectra. Then the other type of binary is an eclipsing binary, just like a solar eclipse. Basically, now this would be where the star, as it kind of scoots around the other star, we see less of the light. If it's either in front or behind the star, we see less of the entire light. So eclipsing binary and spectroscopic binary are 2 ways to know that you have a pair of stars instead of just one. And then we talked about the masses of stars, and earlier we had been talking about stars have different colors. And those different colors we learned in the previous unit was an indication of how hot they are. So here as we have the blue star, you would tell me is very hot, the red star is cooler. Okay, so actually we're going to kind of tie that in. We did that in this unit of material about the sizes actually being even having certain stages, masses, different stars of different masses go through different stages, and they will actually be different sizes if they're main sequence versus a swollen red giant. But anyway, stars as they first start fusing, become a star, can have this range of masses. 0.08 solar masses is the lightest a star can be, and 100 to 150 to even 200 solar masses is the heaviest a star can be. And we use this capital M subscript S as the mass of our sun. This is then showing you, this is not an HR diagram, so don't get confused about this. I know this because we have luminosity, which is the HR diagram, but along the x-axis, instead of having temperature, we have masses of these stars. So you can see the more mass of the star, the greater the luminosity, which, hey, that makes sense. Again, though, this is as they are what we call main sequence stars, I believe. So now finally we move on to the HR diagrams. Dun, dun, dun. You know it's an HR diagram because we have luminosity, again increasing luminosity along the y-axis. And along the x-axis, it's a little backwards. We have hot stars over here on the left and cool stars over here on the right. And you can see the 7 spectral types, O, B, A, F, G, K, M, along the x-axis. Then we have our different groups, and I think I mentioned in class you're going to want to be able to draw this on your, or something like this, on your unit exam. So here we have the main sequence right here, main sequence. Here we have giants or supergiants in this upper right-hand corner. In the lower left-hand corner we have white dwarfs. Again, an HR diagram. Now this actually kind of ties in, we have these little orbs here, even some numbers that go with little orbs, or big orbs, little orbs. These would be the masses of the stars as they are in the main sequence. We have the more massive stars up here, and that makes sense because they're hotter. The lower mass stars here, and they're cooler as they are main sequence stars. But the thing that main sequence stars have in common is they are all fusing hydrogen in their core. All right, then we talked about how stars are born in stellar nurseries in these places called molecular clouds, or sometimes giant molecular clouds, MCs or GMCs. So a lot of stars can actually be born at one time with kind of what we call the same initiation or stimulation of the cloud into these little dense cores. So this actually, remember, if you're looking at a nebula, a molecular cloud is just a big nebula. So as we're looking into this nebula, remember some nebula are dark. So this would be a good example of a dark nebula where there's actually, we have this field of stars around this kind of darker region. This darker region is a dark nebula that's obscuring our ability to see the stars beyond it. So molecular clouds where stars can be born. And then we have this sort of thing where we have different generations of stars. So actually a group of stars can be the thing that stimulates a nebula or within a molecular cloud for these dense cores to be formed. So that's exactly what you're seeing here from left to right. So here we see this could be the parents, okay? And then actually here, these are the baby stars to the right in that fresh molecular cloud of material, where matter can come together and begin these dense cores that can turn into stars. Dense cores can turn into protostars, which can turn into stars. So what happens is this young group actually shines, blows its stellar wind to compress the gas to make these little cores. Isn't that cool? Well, if that's the case, then actually to the left of the young group, you find their parents. And to the left of their parents, you even find their parents. So we actually have generations. There's 1, 2, 3, 4. 4 generations here kind of moving forward, biting into this molecular cloud. I think that is so cool. So stellar nurseries, multiple stars can be born at one time. So we end up with these clusters of stars. So we have 2 types of clusters of stars. We have an open clusters of stars. This is an example. Some of us saw this through the telescope. This is the 7 sisters, or the Pleiades, in the constellation Taurus. Looks like the Little Dipper, right? You can also just kind of see a little bit of the nebulosity. It's just beautiful. So this is an example of an open cluster. Open clusters are generally younger stars compared to globular clusters. So globular clusters are older stars, and actually these globular clusters are located outside the plane of our galaxy in what we call the halo region. So yeah, globular clusters are older stars. Very pretty. All right. Then there is this, where we have these actually protostar, dense cores to protostars. There, you can see the arrows are going from right to left. They are coming on to the main sequence. And one of the things we said is that the more massive stars come onto the main sequence more quickly. I know that takes a long time, compared to the lower mass stars take longer to come onto the main sequence. But whether they're high mass stars or low mass stars, their first stop is to become main sequence stars, at which point they are fusing hydrogen in their core. Now, one of the things about stars, it can be born in clusters, but we kind of have this distribution where within a cluster of stars, the number of low mass stars is much greater than the number of high mass stars. But we see the bright OB stars because they're bright and these guys are so dim. So there's a question on there. I can't remember what the question's about. Again about the limits to stars' masses. The most massive stars are 100 to 150 to even 200 times the mass of our sun. The low mass stars are 0.08 times the mass of our sun. One of the things there might be a question on there is about the idea of a brown dwarf. Remember, a brown dwarf is less than 0.08 solar masses, and that is a wannabe star that never got enough temperature and pressure inside its core to begin nuclear fusion. So we also talked a little bit about finding what we call extrasolar planets. So this is an example of an extrasolar planet. We can't see it, but we can detect it. We can't see it directly, but we detect it indirectly because it actually makes its parent star wobble a little bit. So there's a common center of mass. So because of the presence of this planet out here, this star is wobbling. So, well, it's not wobbling, sorry, it's orbiting a comet. It's orbiting, it's circling, okay? Now, when from our line of sight, if it's just lined up that way, it's moving away from us, we're going to see a red shift. When it's moving towards us, we'll see a blue shift. So again, we can see indirectly that it's being affected by, it's being affected by a mass out here. And so that's one way to see extrasolar planets. The other way to see extrasolar planets would be this way, in which we actually see the planet. Well, we don't see the planet, but we detect that something is moving in front of the star on a regular basis and eclipsing some of the light. So then we talked about, what did we talk about? Well, I don't know if we talked about low mass stars, how they live their lives, and then high mass stars, how they live their lives and their lives. And low mass stars usually are 8 solar masses or lower, but actually I kind of broke off from that and I said if you have something that is from 0.4 to that 0.08 solar masses, which is the lower limit of a star, they are going to do something a little different than their counterparts above 0.4 solar masses. They are going to end up as what we call red dwarfs. And the thing about them is they're relatively light, and that from hydrogen fusion, of course, we have helium. So that helium actually, what we say, convect out from the core, and fresh hydrogen will convect in. So instead of doing what we're going to see here in a minute that other low mass stars do, they end up with actually just kind of a ball of helium in the end. Okay. So here we have now of course, you see an HR diagram. We have luminosity here, surface temperature here, high temperature, low temperature on the right. And now we see these stars leaving the main sequence. And I think one of the things that I've emphasized is that more massive stars, and you guys told me in lecture that more massive stars live their lives more quickly, and high mass live their lives quickly, low mass live their lives more slowly. So that's kind of what you're seeing here, to leave the main sequence. So if you take a cluster of stars and go ahead and put them on an HR diagram and look at their main sequence, the amount of stars that it still has on its main sequence is an indication of its age. So I think in lecture you guys told me that these right here, this would be this is a younger set of stars, and this is an older set of stars because more of the main sequence stars have what we say peeled off to become giants. And we call that the turnoff point. So here's the turnoff point here, and here's the turnoff point here. A lower turnoff point means that actually more stars have peeled off, and it's an older cluster. All right. So one of the terms you're going to see on your test is planetary nebula. So planetary nebula are formed here. As you can see, for instance, if we take something about the size of our sun, after it's done fusing hydrogen to form helium in its core, it is going to go ahead and move here in the giant region, and it's going to have one more gasp. It's going to go ahead and create conditions to take that helium in the core and form carbon and oxygen. and it will be in this area up here. But then actually it's done. It's not going to fuse anything more complicated, and then it's going to go over here and it's going to kind of cool off. It's going to take its material, jet it into outer space, and form this beautiful thing called a planetary nebula. And then actually in the center of a planetary nebula is a white dwarf that's going to cool down and end up over here. Okay, so planetary nebulas are associated with relatively low mass stars. Again, this would be what, between 0.4 and 8 solar masses to create these planetary nebula. And then remember, I said I kind of butchered this guy's name. Chandrasekhar said that your white dwarfs are great, but they actually have a limit to supporting the mass, so it doesn't collapse anymore, and that would be 1.4 times the mass of our sun. And we'll kind of revisit that mass later on. All right, then we looked at high mass stars, and high mass stars would be 8 solar masses up, right? And those guys are going to go out a different way. They're actually going to go ahead and not stop at carbon. They're going to go ahead and fuse carbon to make heavier elements. And with the high mass stars, part of the reason that they burn through their chips so quickly is that they have a more complicated kind of fusion cycle that involves carbon, nitrogen, and oxygen. And this is actually a figure I had that looked at the different types of fusion, core fusion. So in our core, remember, hydrogen fuses to form helium, helium fuses to form mostly carbon, and that's where our star is going to stop and go actually to form a white dwarf. But for more massive stars, carbon will fuse to form neon, neon fuses to form oxygen, etc. And you can see that actually the time scale of these fusions gets shorter and shorter. So at the end, we end up kind of like this looking onion, right? And in the core of the star, right before a massive star blows up, what it has formed is iron from silicon fusion. The thing about iron I have here is that remember that now it's more likely, if you want to release energy, to not fuse hydrogen, but go ahead and fizz it. No, would be nuclear fission instead of fusion to release energy. So kind of talked a little bit about this, that actually in the end, right before the star goes supernova, this would be the star blowing up, it ends up crushing its matter in the core, those iron atoms, and think of those electrons and protons as combining to form neutrons. So it ends up with this like neutron soup in the core, which is pretty darn bizarre. So it might be so that, and this is up to 25 solar masses, so from 8 to 25 solar masses, that object, that neutron soup, is going to end up as a little core, and it's going to end up what we call a neutron star. If it's more massive than 25 solar masses, as it was a main sequence star, then actually even what we call neutron degeneracy can't support the weight of that object, and it's going to collapse to form what we call a stellar black hole. We'll talk more about black holes in the next part. So this whole explosion part happens as there's a stiffening of the object with regard to neutron degeneracy, and so you have matter that was coming in, bumping up against that object and rebounding, rushing up against matter that didn't get the memo, and it's still coming in. So you have matter coming and going, and it's just a crazy time. Now, after the supernova explosion, you end up with this thing called a supernova remnant, and that's what you're looking at here, an example of the leftovers of a star that blew up in an assortment of wavelengths. This is another supernova remnant. This is Messier object number 1, the Crab Nebula. So in the Crab Nebula is a neutron star. And in the neutron star, we know neutron stars are there because they send out, if it works for us, the neutron star is spinning very fast, and just like the Earth kind of has a magnetosphere, it also has a magnetosphere, but at its poles of the magnetic field, it shoots out these rays of energy. So if the orientation is right, we see that ray of energy blip, 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 blip towards us, and so you kind of see these blips down here. We call this signature or signal a pulsar, and it's coming from a neutron star. Pulsar, means neutron star. It's kind of being shown here. Okay, so I think we're going now into material that we're going to cover in this last week here. We're going to talk a little bit about black holes. So one type of black hole is what we call a stellar black hole, and that came from a star that's more than 25 solar masses, as it was a main sequence star. And how can we find these stellar black holes? Well, they give out these signatures most oftentimes in what we call the X-ray region. So you can kind of see, well, there's a black hole here, and this is called an accretion disk. Here's and this over here, this is we said most stars have companions, so this could be a companion star dumping material. There's a stellar black hole here. It is actually getting ready to, kind of like water goes down your drain, and this is called the accretion disk. And as it goes ahead and it goes faster and faster and faster within this frisbee, within this accretion disk around the black hole, it emits X-rays, and you can kind of see energetic material coming out of. Now, I know nothing can escape a black hole, and we'll talk a little bit about this. This is material beyond what we call the event horizon, leaving the stellar black hole. So in order to understand black holes in general, again, stellar black holes are not the only type of black holes. We need to understand, or we can visit some of the things that Einstein postulated. And so Einstein says that we could have a black hole. I'm trying to come up with what I'm saying here. We could have a black hole that's more than 25 solar masses, as it was a main sequence star. The object that falls in on itself, actually, that little kind of corpse of the supernova event, is 3 solar masses. That ultimately neutron degeneracy can't stop its falling in on itself. Actually, black holes end up being kind of a hole in the fabric of space-time. I know, it's crazy. So let's look at a little bit of what Einstein postulated with his different theories. As we talk about black holes, they are an especially dense object that affect motion, distance, time, and mass. So you'll hopefully kind of see how this relates to black holes. But Einstein said, according to his special theory of relativity, that with regard to length, we have this thing called length contraction. And it has to do with if you are you have to have a stationary person, and then you have to, that's the frame of reference of that person, that could be you. And then you have actually another frame of reference that is that stationary person can see. So it goes something like this. Literally, if a train has a certain length when it's at rest, you can kind of see the length of this train when it's at rest. When that train starts moving, I'm not moving, the train is moving, actually its length contracts. Okay, now this actually motion, the faster it goes approaching the speed of light, which is a really fast train, the more its length contracts. When it gets to the speed of light, its length is 0. I know that's crazy, but it's been proven. Now, the interesting thing is, there's a lot of interesting things, but if you are on this train, your frame of reference, actually the train's length is the same, but from an outside observer, the length of the train shortens. Okay, again, with regard to motion now and time. If you are, and actually they've proven this on planes, if you are in a plane flying fast, now not the speed of light obviously, but if you're flying fast, your clock will actually run more slowly than the person who is in a stationary reference. Okay, so the faster you go, time goes more slowly, and it's true. And that has consequences, right? The other thing is that, again, with regard to moving fast, objects moving fast, and mass, the faster you go, the more mass you have relative to a stationary observer. Whew. Okay. The fabric of space-time can be kind of thought of as like a sheet like this. So we think of space and time being separate, but according to Einstein and his proven theories, they are actually intertwined. So an object on space/time, such as this paperweight, can actually make a dent in the fabric of space and time. Okay. So Einstein's general theory of relativity then looks something like this. It has to do with, in this case, I'm showing the effect of gravity on time. The more gravity, as indicated here by the Earth versus the Moon, the more gravity an object has, then the more slowly time unfolds. So for instance, a clock here on the Earth versus a clock here on the Moon, notice that the clock here has unfolded 20 minutes versus the Moon is 25 minutes. Okay, so that's due to the effect of gravity and time. I know. There's this other thing then with regard to gravity, and it's called gravitational redshift, and it can be demonstrated by this. Here, these little blue orbs are all white dwarfs, which are very dense objects. And here we have a, I'm going to kind of start, if it's okay with you, from right back to left again. Here we have a light. We have a light that is a certain distance from the white dwarf, and it is shining yellow. If we take that light and make it go closer to my white dwarf, as you're going from right back to left again, notice what happens is that the photons, because of the influence of the gravity of the neutron star, actually lose energy as they leave the neutron star. So here it's yellow, here it's orange, here it's red. It's called gravitational redshift due to the gravity of that dense object. Speaking of dense objects, then a black hole is a few features about a black hole. I'm trying to think of what you might have on your test. A few features about a black hole. The singularity is the point where all the matter has basically collapsed in on itself, creating that kind of what I call tear in the fabric of space and time. That's the singularity point. Now, black holes are, that would be this D down here. A black hole is such that if you take a photon and try to leave the surface of a black hole, it won't have sufficient speed to actually leave the influence of the gravity of a black hole, and you can kind of see it curving back down. Here, a neutron star, you can see that if you have the right trajectory, light can leave, okay? And white dwarfs, of course, light can leave. You see it sort of bent, and a normal star, you see light just leaving. So with regard to a black hole, I kind of have in italics here that light from a black hole flying at an angle will go back towards the black hole, but if it's flying straight up, that energy will cease to exist. That's kind of cool. Okay. So here's the anatomy of black hole. I mentioned singularity. Event horizon is the region around singularity, beyond which, or closer to singularity, nothing can escape the influence of the black hole, even traveling at the speed of light. So the Schwarzschild radius then is the radius or the distance from singularity out to the event horizon. One of the things that black holes can do, according to Stephen Hawking, which is amazing, is black holes over time can evaporate, and we call that evaporation process the Hawking process. And so smaller black holes, it kind of is an acceleration sort of process. So the smaller the black hole gets, the faster the evaporation or the Hawking process is. As it evaporates, you can see that it kind of has a series of particles. So that's the Hawking. That's the Hawking process, the evaporation of a black hole. And according to this, then at the very end, it has an explosion at the end as it finishes evaporating. So one of the cool things I think is this idea of spaghettification. And in lecture, we're going to talk about how if you were, and I don't suggest it, going to fall down through the event horizon of a black hole, as you approach the event horizon, actually your body would be stretched to the point of being single atoms that are going in line, and so that extrusion process is called spaghettification. Ugh. Okay. So in search of black holes, there actually has been definitely some things going on this fall about this. This is a photo of LIGO, and it is detecting the influence of black holes in the fabric of space and time, make these ripples. And those little subtle ripples can be detected by LIGO, and it's so amazing. This is a figure I had earlier. This is a figure from your, oops, sorry, I guess it didn't make it. Anyway, there's a figure from your textbook that has kind of green around it. I think that's neat. So I guess here I need to say gravitational waves are an indication of black holes on the fabric of space-time, something like that. So one last thing I want to talk about is this part about companion stars and things that can happen. A nova, not a nova, but nova event, N-O-V-A, actually can reoccur. Nova event is kind of described here, where we have, this is, of course, you guys would tell me it's a red giant. Over here we have a white dwarf. So nova event can only occur when you have a white dwarf. The white dwarf has a companion star that's nice and swollen. So you see the companion star dumping material onto the retired star, and what can happen is basically the material builds up and to the point where nuclear fusion can occur just kind of on the crust of that star, kind of a blanket of material. And that nuclear fusion begins kind of just explosively. It's kind of a burp, and it just kind of blows off its blanket, and then the material can dump again on the retired white dwarf, and you can get another nova event. So nova can reoccur. This, though, cannot reoccur. We actually have a second type of supernova event called a supernova type 1A. And again, we have a retired white dwarf star, and here we have a swollen red giant. The difference between the nova event and the supernova type 1A event with the white dwarf is that the matter doesn't, like just as a blanket, begin nuclear fusion on the outside and kind of blow it off. Actually, kind of, it's more of a whole sort of thing, where the mass of the star, the white dwarf, exceeds that Chandrasekhar limit, and in that point it actually tries to begin nuclear fusion in its core. So it's more of a again, it's a bigger, hairy deal. The nuclear fusion in its core, the awakening, actually then kind of blows the whole white dwarf up. So these do not reoccur. Neutron stars in a close binary system. So again, so this is different. I know it's the same figure, but you're going to have to use your imagination that instead of a white dwarf here, put NS for neutron star. So we can actually get the signature from a neutron star of, remember how with black holes I called it an accretion disk? Again, we have an accretion disk of material around here, and that material can create these cute little, not cute little, but these little X-ray bursts in that accretion material area, and that's an indication of a neutron star that's getting matter from its buddy and kind of burping like that. That's it.